Hello guys, today we'll be reviewing topic D.4 in the IB Physics HL syllabus, which is electromagnetic induction. So, what is induction? Well, induction is simply when something moves perpendicularly to a magnetic field. So let's assume these are magnetic field lines. Sorry. And something moves this way periodically, so it goes back and forth. So what we call this, it's cutting the magnetic field lines. So this cutting of the magnetic field lines actually creates a current or an induced EMF. But first, we must define something important known as magnetic flux density. The magnetic flux density is the total magnetic field B, which we know in Teslas, in a given area, given meter squared. So it is the total magnetic field in a given area. And its units are either Tesla meter squared, so we're combining both units, or a new unit here, you don't have to know it, but it's Weber, sorry, denoted by a large W. Okay, so what is this importance? So we state when something cuts into a magnetic field, the magnetic field, the area or the magnetic field changes. B starts to change because this is moving through areas within the magnetic field. So we created a new law called Faraday's law, which states that the induced EMF or current, but here it's EMF, so in volts, equals negative N phi divided by T and delta phi delta T. Negative N here if you're only dealing with a coil. So N is a number of turns of a coil, but it can you don't have to use it if you're not using a coil. So we're basically saying that the EMF is equal to delta phi over delta T, and you know that delta phi is equal to BA cosine theta, so it's basically equal to delta BA cos theta divided by the change in time. And what you would notice here is actually that the EMF is equal to d phi by d theta or by dt. And if you don't know this is the derivative. So we can say that actually the EMF is directly proportional to the derivative of the magnetic flux, or the EMF is directly proportional to the rate of change of magnetic flux, since that's what a derivative means. Okay, another equation we have here is if you have a moving, I don't know what to call it, but a moving metal plate, you could say, with a certain length, L, moving through a magnetic field or cutting a magnetic field, and it is moving at a given velocity V, and a magnetic field of strength B. So the EMF here would also be given by BVL, where this is the length, this is velocity, and this is again the magnetic field strength. Yes, simply. So you could see here that this is equal to BA cosine theta in a way, since velocity times length when at a rate of I'll tell you how. Okay, let's derive it. So let's say EMF equals BA, and let's assume cosine theta equals 1 over time. Well, when something moves through an area, or let's simplify, BA, we can also say that this is Displacement multiplied by some length over time. Displacement over time is velocity, so we get BVL. Now, this is a very short, actually very short topic, so I'll start solving questions. First question states, define magnetic flux and explain how it relates to Faraday's law. Well, we just stated that the magnetic flux is the total magnetic field in a given area. And it relates to Faraday's law of induction, or actually, I forgot to tell you, this law is known as Faraday's law. So just know. It relates to Faraday's law of induction that the rate of change of magnetic flux is directly proportional to induced EMF. Let's go. A coil with N equals 50 turns. So here it's a coil, so we use N. And an area of 0.02 meters, A equals 0.02, is placed in a uniform magnetic field, B equals 0.3. The coil is oriented such that the plane of the coil is perpendicular to the magnetic field. Calculate the magnetic flux through the coil. So this is actually a trick question. So let's calculate the magnetic flux here. Equals B 0.3 times A, which is 0.02, times cosine 90, because it's perpendicular. Oh, sorry, it's actually cosine 0. When it's perpendicular, it's cosine 0. So cosine is 1, so we get 0.3 times 0.02, which is equal to 0. I'll get my calculator. 0.3 times 0.02 equals 0.006, and it is in Tesla meters squared. If the magnetic field drops uniformly to 0 in 0.1 seconds, calculate the magnitude of the induced EMF in the coil. So what does it mean to drop into 0? It means that it's rotated theta equals 90 degrees, or pi over 2. Okay, so it's telling us we already have the magnetic flux density, and he's giving us a change in time, and we have the number of turns, so EMF equals negative 50 times 0.006 over 0.1, which will equal 3 volts. Okay, yes. Oh, we don't have generators here. Okay, what are the units of magnetic flux and magnetic field strength? So the units for magnetic flux: A, Weber per meter squared; B, Weber; C, Weber; and D, Tesla meter squared. So we know it's either Tesla meter squared, not per meter squared. So, and we know it's also Weber. So it is either B or C, but we need to know the unit of magnetic field strength. So it is either Tesla or Tesla per meter squared. So we know that the unit for magnetic field strength is Tesla, so it's B, which states that the magnetic flux is in Webers, and magnetic field strength is in Teslas. Okay, the magnetic flux phi through a loop of wire is increasing at a constant rate. What happens to the induced EMF in the loop? The induced EMF increases as the flux increases. The induced EMF decreases as the flux increases. The induced EMF is constant as long as the rate of change of flux is constant, or the induced EMF alternates. So, if you know the law, we know that the induced EMF is directly proportional to the rate of change of magnetic flux, and here it states that it's increasing at a constant rate. So if the rate is constant, then the EMF must be constant, so that would be C. Trying to find questions, sorry. Okay, let's go here and try to find the question. Okay. I'm trying to find, sorry, it's taking, and there aren't many questions on this topic. Okay. Well, I can't find many questions. These are the type of questions you'll find in your exams. So thank you, and I'll see you in the next video.